In 2020, the automotive industry appeared to be hitting fast forward. Electric vehicle sales were doubling, and Level 5 fully self-driving cars seemed imminent. By 2024, that trajectory changed. Consumer demand in the US and Europe softened, and manufacturers realized that electric vehicles represent a massive margin and infrastructure challenge. The dream of full autonomy also stalled. Development is now constrained by unpredictable edge cases, safety validation complexity, and strict regulatory limits. The revolution didn't die, but it hit a hidden hardware bottleneck that the public couldn't see. Before 2020, cars were primarily physical, mechanical machines built around distributed systems. The engineering approach was simple. Whenever a car needed a new feature, engineers added a dedicated electronic control unit, or ECU, to manage it. Over decades, this additive process resulted in modern vehicles carrying between 70 and 100 disjointed mini-computers. This fractured intelligence manifested as a heavy, chaotic web of wiring harnesses attempting to connect every individual sensor and motor. Dumping the massive data loads of modern EVs and smart sensors onto this archaic 100-node system broke the traditional car architecture. Modern engineering now manages two massive strains simultaneously. First is the EV platform, where the battery alone accounts for roughly 40% of the vehicle's total cost. Managing the hardware complexity of power electronics and thermal systems in real time requires constant, high-speed calculation. Second is intelligent driving. Instead of chasing full autonomy, the industry pivoted to scaling Level 2 features across the board. This relies on a dense sensor stack, consisting of dominant cameras, mandatory radar, and selective LiDAR, all generating gigabytes of data every second. Managing high-voltage thermal data alongside this sensor intake makes the legacy, scattered computing model obsolete. Automakers responded with the Great Consolidation, reducing the ECU count by shifting to centralized domain or zonal architectures. This architectural shift turns the vehicle into a centralized supercomputer on wheels. Networking all critical driving functions into a central digital brain exponentially increases the attack surface for hackers. This risk triggered a surge in global regulations, making strict cybersecurity and functional safety standards like ISO 26262 mandatory by law. Because vehicles are now connected systems, product integrity and rigorous safety protocols are the core of the product. Since 2020, cars transitioned from mechanical, distributed machines into software-driven, centralized, and safety-critical systems. Automakers now face the challenge of safely integrating the physical EV platform with the digital ADAS brain. Looking toward 2030, demand is declining for pure mechanical complexity and traditional ECU-level development. The industry now requires massive investment in systems engineering, AI software, functional safety, and cybersecurity. The EV defines the platform, and ADAS defines the intelligence, but the winners will be those who can safely